For this lesson, we're going to be continuing with our study of the transformations of functions. Just as we have before, we're going to start off with a reminder that you should have seen this before in terms of a very specific function, in terms of a parabola. So if we think of a parabola in vertex form, because this is such a graphic intensive page, it's not going to let me write. If we think of a parabola in vertex form, it's going to end up having an equation that looks very much like this. So this idea of vertical stretches, reflections, compressions, the idea of shifting left and right, particularly of the position of the vertex, the idea of shifting up and down, those should all be at least somewhat familiar ideas. Now, I'm not going to be doing notes on this. This is actually a screen capture of the worksheet that I also have available on the web page. So you could go and download that and then work through this at your own pace. What I'm going to do is I'm going to take the time to go through the examples or exercises that I have listed on this worksheet. And the purpose of this set of exercises is to focus on some horizontal transformations. In particular, they are horizontal transformations that are probably unfamiliar to those of you who came to this course from the grade 10, the 2D course. Horizontal reflections, horizontal compressions, and horizontal stretches. Now, the reason why these are unfamiliar is because in the case of a parabola, these three transformations are unnecessary. They can be taken care of in other ways. Specifically, they can be taken care of vertically, or because of the symmetry of a parabola, a horizontal reflection doesn't actually have any visual impact on a parabola. But now that we're talking about more types of functions, today we're going to be looking at primarily the radical function, the square root, then these things do start to show up. So I would encourage you to go to the web page or the handout that I provided you in class and go through that on your own. What I'm going to do now is I'm going to work through those examples in an easier to read form. It's going to be a larger scale. So here's what I was talking about before. Hopefully you have the background so that the idea of a quadratic relation in vertex form is familiar to you. If we say that f of x is equal to x squared, in other words, we are defining our function to be the quadratic function, then I can take these same transformations and I can apply them to the function. So for example, if f of x is equal to x squared, then f of x minus h is just x minus h all squared. Then I multiply by a, and then when I have my result from that, I add k. Now, something else that we're going to be doing more and more of in this course is we're actually going to be making different use of the parameters. A is going to stay the same. That's going to be the leading coefficient. Instead of h and k, we're going to be using p and q for our shifts, and that's another way of thinking. So that means p and q are going to represent the x and y coordinates of the vertex. And then I apologize for this. Confusingly enough, we are going to repurpose the parameter k, and it is now going to be the parameter that controls horizontal reflection and scaling. Now, to be honest with you, the choice of these parameters is completely arbitrary. They are like our let statements. Let A represent such and such. Let P represent, let Q represent, let K represent. So all we have to do is adjust our thinking and remember that these things have new definitions. The same thing is true for variables. I know we don't take much time to think about this, but the fact that we use x for the independent variable and y for the dependent variable, that is also an arbitrary choice. We've certainly seen in this course, and probably in previous courses, you may have seen questions where you had a distance in terms of time. And that's just a redefinition. Now you're saying that the independent variable is represented as the letter t because that's convenient. It represents the concept of time. The dependent variable is now represented by the letter D, and that's convenient because D stands for distance. So that's all we're doing now with this new way of writing, except for now we're using P and Q, for example, as the X and Y coordinates of the vertex. Okay, so you might want to have that worksheet printed off to be able to refer to. I would actually encourage you to try the worksheet on your own first, because then you'll be able to make a little bit more sense. I would rather you follow along and try to find your mistakes as opposed to just looking at this blindly. Okay, so we are going to graph f of negative x. So this is the first time we've introduced a negative inside the function bracket. And instead of working with parabolas, for this lesson we're going to be focused on the radical function, square root of x. So first of all, just over here at the side, I don't want to jump around too much. If f of x is equal to the square root of x, then f of negative x, wherever I had an x before, I replace it with negative x. So I end up with this. So the first thing we're going to do is create a table of values for the parent function, so x and square root of x, just to remind you of what that's going to look like. So typical, when we're graphing the radical function, we're typically interested in perfect squares. That's going to make for an easier graph. So I'm actually going to do positive and negative perfect squares. Now you might be puzzled why I'm doing this, because quite obviously these values are no good for what we're doing here. They all result in, essentially, I have chosen values that are inadmissible. I cannot put -9 in here. The square root of -9 doesn't give me a value that makes any sense. So what I end up with is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. And so far, what I have essentially is I have between here and here, actually, I could keep going to larger values. These are all good, and everything from here backwards is no good or inadmissible. And if I do this with the parent function, I end up with this graph, which we've seen before. This is the graph of y equals the square root of x. But we're not going to stop there. What I'm going to do now is I'm going to say, okay, what about taking f of negative x, which is the square root of negative x? Well, now these values, this is the reason why I wrote this out. When I take the square root of -9, a negative times a negative becomes a positive. That becomes the square root of 9, which is equal to 3. The square root of -4, so the negative of -4 is just equal to the square root of +4, which has an answer of 2. The square root of -1 is equal to the square root of 1, gives me 1. Square root of 0 is not a problem. Square root of 0 is simply equal to 0. And now we get into the square root of -1. So it's the negative of 1, which of course is the square root of just -1, which now becomes inadmissible. And here I have the square root of the negative of 2, which is of course the square root of -2, which is inadmissible. And we end up with the square root of -3, which is inadmissible. So you can see that now, for this function, for the square root of -x, the values that I'm allowed to have are actually all of these values, because I'm automatically taking the negative of the independent variable. Then these are the good values now, and these values become the ones I'm not allowed to have. So that's going to change my graph. It's going to change my graph quite a bit, actually. So let's go ahead and take a look at the graph. So now in the original parent function, I had positive values which were okay, but that's not going to work anymore. This value at 0, 0 still exists, but now we go to -1 and +1. That gives me a point here. And then at -4, it's negative of -4. So just going back to my table of values, when I had an x value of -4, I actually ended up with a y value of +2. So an x value of -4 gives me a y value of +2. And an x value of -9 gives me a y value of +3, pardon me. And so my new graph looks something like that. I know I didn't do a great job. I didn't quite hit that point, but believe me, it's hard to draw these things nicely, especially using this stylus. Now, what do I want you to take away from this? What has happened? Visually, I think you can see that compared to our original graph, our new graph, our image, is actually a mirror image. A little bit more specifically, what I'd like you to see is the fact that this first point, which was the point 1, 1, well, where has it gone? It has gone over here to -1, 1. Notice that the x-coordinate has changed from 1 to -1, but the y-coordinate is the same. And we could do the same thing. This point is the point 4, 2, and this is the point 9, 3. And now, where have those points gone? This point 4, 2 has gone over here to -4, 2. The x-coordinate has been reflected. It's gone from +4 to -4, but the y-coordinate is unchanged. The x-coordinate has been reflected to -9, but the y-coordinate is unchanged. And so f of -x as a transformation is what's known as a horizontal reflection. Sometimes you'll hear people refer to that as a reflection or a mirror image in the y-axis, but I usually will say horizontal reflection. All right, so now we have y equals f of 4x if we started with this. So that means we're looking at y equals f of 4x. Instead of f, I think of the function, which is the square root function, but wherever I have an x, I have to write 4x instead. Now, something that's interesting here, if you think about our work on radicals so far, you might recognize that, well, hold on a second, 4 is a perfect square. I can actually write this as 2 times the square root of x. These two things, if you do it this way, these are known as equivalent expressions or equivalent forms. So these two things, they're still the same graph, they're still going to give the same result, but we already know what this means. We know that this is a vertical stretch by 2. Now, this is not what I want to focus on right now. I'm focusing on the horizontal. So because I want to focus on the horizontal, I want to leave this 4 inside the square root, because when the parameters, in this case value 4, when the parameters are inside the functional bracket, that's a horizontal transformation. So this is an interesting observation, and I'm going to come back to it again in a moment, but I just want to make sure we are focusing on this one. So I'll tie these together when we take a look at the graph. Okay, so once again, standard x values, -9, -4, -1, 0, 1, 4, 9. Okay, so I'm going to take the square root of x, which is the parent, and I'm going to take the square root of 4x, which is the transformed function. Okay, the square root of x, so we end up with inadmissible You know what? I'm just going to leave those, make this a little bit easier rather than writing out. I'll just do this. I'll just stroke those out for now. 0, square root of 1 is 1, square root of 4, square root of 9. Now, what about multiplying by 4? Does that make this any better? No, it does not. That becomes the square root of negative 36, which is still inadmissible. The square root of this one, negative 4 times 4 is negative 16. That's inadmissible. And so, and I might as well write the last one out. This becomes the square root of negative 4, which is inadmissible. Now, what is the square root of 4 times 0? Well, that's still just the square root of 0, which is equal to 0. What is the square root of 4 times 1? Well, that's equal to the square root of 4, which is equal to 2. The square root of 4 times 4, remember we're multiplying by the x values here, not by these y values, by these x values. That's the square root of 16, which is equal to 4. And the square root of 4 times 9 is equal to the square root of 36, which is equal to 6. So for my x coordinates 0, 1, 4, 9, I end up with y coordinates 0, 2, 4, 6. And let's see how that compares to the parent function. So 0, 0 is still a point. At 1, I used to have a point at 1, 1, but now I have a point at 1, 2. At 4, I used to have a point at 4, 2, but now I have a point at 4, 4. And at 9, I used to have a point at 9, 3, and now I have a point at 9, 6. And I do my best to draw a nice smooth curve through those points. And if you take a look at this, it is very tempting to look at this in terms of a vertical transformation. I used to have the distance from here to here used to be 1, and now I can see that the distance from here to here is 2. The distance from here to here is 2. And not surprisingly, now the distance to that point is 4. So the size of these vertical steps has doubled. And that goes back to what I said here, which is this is a horizontal transformation, but it can also be viewed as a vertical transformation. In this case, it can be viewed as a vertical stretch by 2. That's what I just pointed out on the page. Sorry, I went the wrong direction there. So if that's not what I want to look at, well, what is it that I do want to look at? What I want you to see instead, if I can back those off, instead of focusing on points that are lined up one on top of the other, let's look at points beside each other. Now it's much harder to see. To be honest with you, we've only got a couple here that we can see, but I just want to illustrate it to you, which is this one is the easiest one to illustrate. So we go from there to there. So how far away was this point to begin with? This point was 4 units in this direction. And now how far away is this point from the y-axis? It is only 1 unit to the right. So going from 4 units out to 1 unit out, well, what kind of transformation is that? It is actually 1/4 of the horizontal distance. So let's look at it in terms of coordinates. This one was the point 4, 2, and this one is the point 1, 2. So how did we change from the 4 into a 1? And the way we did that is we divided by 4. So this 4x, 4 times x, turned into taking the x coordinate and dividing by 4. And so I want to go back and relate this one final time. With a vertical stretch or a vertical transformation, this number 2 meant multiply by 2. Okay, so a vertical stretch by 2. That means take the y coordinate and multiply by 2. This number is a horizontal compression, and it means take the x coordinate and divide by 4. Now that's strange. It's going to take a little while for you to adjust to that. So when we're outside of the function, then we multiply. That's what our scale factor does. When we're inside the function, our scale factor means division. So bigger numbers actually result in a compression. And as you might expect, a smaller number is going to result in a stretch. And so let's explore that as well. So I understand this is tough to see. This is you have to really focus and get your head wrapped around this. Okay, so now let's go and take a look at that other case. So once again, here's x. Here's the square root of x. So -9, -4, -1, 0, 1, 4, 9. Square roots, I'm not going to take any of those negatives. 0, 1, 2, 3. Now, y equals f of 1/4 x. My function is actually square root, and wherever I add an x, I'm going to put 1/4 x. Now we could also, so I'm going to separate this, maybe say, or what is the square root of 1/4? The square root of 1/4 is the same as 1 over the square root of 2, so this is the same as 1/2 square root of x. Well, what kind of transformation is this? This would be a vertical compression by 2. So now that I've said that, what do you think this one is going to be? And we'll come back to that. So now let's go ahead and graph 1/4 of x. Now this is actually going to end up being kind of awkward, so I'm going to inject something else here. Now first of all, the negatives, still not doing those, because 1/4 of a negative is still a negative number. 1/4 of 0 is equal to 0, so that's equal to 1/4 of 0 is just the square root of 0 is equal to 0. 1/4 of 1 is just equal to the square root of 1/4, which is equal to 1/2. That's okay, we can graph that. 1/4 of 4, which is this value, 1/4 of 4 is just equal to 1, and that's square root of 1 is 1. That works. This gets a little awkward. 1/4 of 9 square rooted is equal to, another way to write it would be 9 over 4 square rooted, which is equal to 3/2, which is, I mean, that's doable. That's 1.5. It's not so bad. And then I'm going to add another point on the end here, which is 16. The square root of 16 would just give us 4, but the square root of 1/4 of 16, well, 1/4 of 16 is just equal to 4, and the square root of 4 is equal to 2. So we've got some points here that we can definitely graph. So I've modified this graph to go out to 16. So now we still have, let's just put these on here, we still have the point 0, 0. So remember, we're using this one and this one. So this is the x 0, this is the y 0. So that gives us a point here. Then we have the point 1, 1/2. So the point 1 and now 1/2 is going to be here, right in the middle of my grid. Then we have the point 4, 1. That should be easy to graph. 4, 1 is there. Then we had, and I'm not going to go back, then we had 9. 9 is right there. And 3 halves, which is 1.5, which is right here. And then we had at 16, we had 16, 2. And again, this is going to be challenging to get a nice curve here, but I'll do my best. I'll give that one more try. Not that much better, but it will have to do. Okay, so once again, there is a very reasonable temptation to take a look at these vertically. And if we do that, if we take a look at these vertically, what we end up with is the connection that I already made with the equation, which is that all of the new points have y coordinates which are half as high as the old points. But that's not the transformation that we're looking to observe here. It's a valid transformation. It's just not the one that we want. The one that we want is a horizontal transformation. So I'm going to take out those verticals, and now I'm going to say, okay, can you make the same connection horizontally? All right, well here I have 2 points that are lined up with each other. This first point is 1 unit away from the y-axis, 1 unit to the right. And this second point is how many units? 4 units away. We actually have 2 horizontal points lined up with each other here. And when I say horizontal lined up, it just means the y-coordinate hasn't changed, because there was nothing here that should have changed the y-coordinate. So now we have our first point, our parent function, was 4 units away, and the other point, the transformed function, is 16 units away. So we ask ourselves, what turns 1 into 4? What turns 4 into 16? So how do we change from 1 into a 4? How do we change from a 4 into a 16? And of course, to make these changes has to be the same operation. And I think you can see pretty clearly that that's a multiply by 4. But how does that relate to this value, 1/4? So what we've actually done is to multiply something by 4 is the same as, and that's what this gives us, is the same as dividing by 1/4. Because let's take this value of 1. 1 divided by 1/4 is another way you could write this as 1 over 1/4, which is equal to 1 times, we multiply by the reciprocal, and you can see, well, that's just 1 times 4, which is equal to 4, which is the answer we got right there. So when we had a larger, as in bigger than 1, when we had a larger value for this parameter, it caused a horizontal compression to occur. And when we have a smaller value of this parameter, and smaller means, in this case, between 0 and 1, it actually causes a horizontal stretching to occur. So the result of the horizontal scale factor is opposite to what you'd expect from the vertical. And that is actually something that we have already dealt with. And I think I've got that here. I can refer to it here in our summary. The thinking behind that, so the fact that this means we're going to divide by k, that's the same as the fact that this is written x minus p, but that would be a shift to the right by p. So if we have something that said x minus 5, we would know that the minus 5 means actually go right by 5. Whereas here, if we had minus 5, that would be down. So the vertical parts, which I'm marking on blue here, The vertical parts, the numbers do exactly what you'd think. A big multiplier results in big values. A positive number means shift up. Here, everything is opposite. A big number for k actually means create smaller values because it's compression, and a negative value, x minus 5, actually means shift to the right. There's some things that are going to take some getting used to there, but that's pretty much the case, and that's why we do lessons. Okay, good luck with that work.